us see how the following statements are equivalent, which these statements we were used in the definition for normal extension. So for normal extension, we had said if any one of these three conditions they are satisfied, then we say that the given extension forms the normal extension. So the statements are, if E is given to be an extension field of F, this is given to be an algebraic extension field of F, which is contained in an algebraic closure F bar of F. We have some algebraic closure F bar of F. So this E is contained in this one. Then the following conditions are equivalent. Firstly, it says every irreducible polynomial in Fx that has a root in E splits into linear factors in E. The second condition is that E is the splitting field of a family of polynomials in Fx, and the third statement says every embedding sigma of E in F bar that keeps each element of F fixed maps E onto E. And in other words, this mapping sigma, this could be regarded as an automorphism of E. What is an automorphism? Automorphism is an isomorphism which maps the same set or field to the same set. So this mapping goes from same set to the same set, and it is an isomorphism. That means it is 1, 1, it is onto, and it is a homomorphism. So this is given to us, right? So for showing these statements as an equivalent statements, we will prove that the first statement implies second statement. So firstly we'll assume first is true and we'll prove the second. And then we'll first show one implies second, then we'll show second implies third, and then we'll show third implies first. So all these statements would be equivalent to each other if we prove it in this way. So firstly, let us suppose first statement is true. First statement says that every irreducible polynomial in Fx that has a root in E splits into linear factors in E. So this is given to us, and we wanted to prove that E is the splitting field for the family of polynomials. So now we are given that any polynomial in Fx has a root in E. So let alpha belongs to E, and because in the statement it is given that E is algebraic over F, that means alpha is algebraic over F. If alpha is algebraic over F, then P alpha x be its minimal polynomial, because for every element here in this extension field E, we have some polynomial here Px which belongs to f of x, such that the alpha is the root of this polynomial. That is the definition for algebraic element alpha. So if alpha belongs to E and E is algebraic over F, that means the element alpha is also algebraic over F. That means corresponding to this element alpha, we have some minimal polynomial over F. So this polynomial P alpha x, this splits into linear factors in E. Now because the element alpha, that was an arbitrary element, so we can say this is true for any element that you take from E. So that means you say E is the splitting field for this family P alpha x, where alpha belongs to E. Because alpha was any arbitrary algebraic element which was present in E, and for each alpha we have some minimal polynomial such that it splits into linear factors. So thus we found one splitting field E of the family of polynomials P alpha x. So in the second part we shall try to prove that second implies third. So we assume that E is the splitting field of this family of polynomials, and we wanted to prove the third point. Third point says that we wanted to prove there is an embedding sigma of E in F bar such that each element of F fixed, keeping it as fixed, maps E onto E. So this is what we are trying to prove here. So for that we assume that alpha belongs to E be any element of this Fix. So what we do, we now create an mapping sigma from E to F bar. What is this F bar? This is the closure of F. This is any embedding. So we assume that this is 1, 1 and this is homomorphism. then this mapping, when restricted over F, acts as identity. So that means we are saying whenever you take, because E, what is this E? E is an extension field of F. So E has more elements than the elements present in F. So if we take only the elements that are present in F, this is E and this is the portion of F, and these are some extra elements which are present in the embedding, right? So now if we take the elements which are only present in this F, that means we restrict our mapping sigma to F such that it now acts as identity mapping and it is an embedding. Then sigma of alpha, that is a root of Fix. Why? Now sigma of alpha, that means we have considered alpha from E, that was an element of E, and when you apply alpha to it, sigma to it, you have this element as present in F bar. So now, because every sigma is a homomorphism, that means sigma, this maps, sigma being a homomorphism maps its root to another root, right? And because it belongs to F bar and this is the algebraic closure of this, so that means we can say sigma alpha belongs to F bar, that is algebraic in nature. Now this is algebraic, so we say it is a root of some polynomial which is present in F. Thus it is a root of some polynomial Fix which is present in F. But since E is generated by the roots of all the polynomials Fix, therefore this sigma of E is contained in E. Why? Because sigma E was a root. Therefore, from here we can say that sigma from E to E is an embedding. This is an embedding of algebraic extension. This is an embedding of algebraic extension. And we know that whenever we have an embedding of an algebraic extension into an algebraic extension, that mapping is onto. If this is onto, this is what we were trying to prove, that this is an onto mapping. So next thing that will prove that third implies first. So the third part says, now we assume that third part is given to us and first part we have to prove. So for that what we do, we assume some polynomial p of x in f of x, and we assume this to be irreducible polynomial, and if this is an irreducible polynomial over f, that means it would have a root alpha in E. So now what we wanted to show, that every irreducible polynomial in fx that has a root in E, this splits into linear factors in E. This is what we are trying to prove. That means if we prove that if one root is available in that particular extension, then other roots are also present in that particular extension. So we assume one root alpha which is present in this E. So one root alpha which is present in E of this polynomial p of x. So now we say this beta is some other root of px, and if we show that this beta, this belongs to E, we will prove that every root, if one root of polynomial is present in that, every root of that polynomial is present in px. So px will split into linear factors in E. This is what we are trying to show. So we will show that this beta belongs to E, That means all the roots of Px will belong to E and the polynomial will split into linear factors in E. So now we have two roots alpha and beta of the same polynomial. So what we can do, we can create an F isomorphism such that we have F of alpha isomorphic to f of x divided by the maximal ideal generated by Px, and this is further isomorphic to f of beta. So by transitivity, this f of alpha would be isomorphic to this f of beta. So we can define a mapping sigma from f of alpha to f of beta, which is an isomorphism because these two are isomorphic to each other. If they are isomorphic to each other, that means sigma of alpha would be equal to beta and sigma of A is equal to A for all sigma belongs to A. But we also know that this mapping sigma defined from f of alpha to f of beta, this could be extended to an embedding sigma star from E to F. You'll see that why we have done this in a moment. So this could be embedded. This is from a previous result which says that any embedding could be extended to another extended which maps the extension field to the other field. So using the given result which we have assumed here, that every embedding sigma of E in F bar keeps each element of F fixed which maps E onto E, this sigma star is an automorphism of E. That means sigma star from E to E is an isomorphism because it maps the same field to the same field. So in this case, sigma star alpha, what is that? It is an automorphism. So this, because this is an extension field of sigma, so we can write sigma star to be sigma. So we have sigma of alpha, and we know sigma of alpha, that is equal to beta from this F homomorphism, F isomorphism, right? So from this F isomorphism, F of sigma of alpha, that is equivalent to beta. So from here we have this equal to beta, and because sigma star E, sigma star alpha, alpha was here in E, so sigma star alpha, that would be again in E. So because this is in E, this is equal to beta, so beta would also be in E. If beta is in E, that means we say all the roots of this Px are there in E. If all the roots of Ex are present in E, we say that the polynomial splits into linear factors in E. So this is what we have proved. So thus we have shown that the first part is true whenever third part is true. That means whenever we are given that embedding sigma of E in F bar which keeps elements of F as fixed, and it is given to be an automorphism, in that case every irreducible polynomial in Fx that has a root in E splits into linear factors in E.